How to determine the nodal displacements of a one-dimensional bar element using finite element approach. Let us discuss with this problem. Okay. Consider a circular bar of Young's modulus E is equal to 200 gigapascal as shown in the figure. Calculate the nodal displacements. So here a stepped bar is given in the problem which is fixed at both of its ends and it is subjected to an axial load of 2 kilonewton in this position. To follow finite element equation to solve a structural problem, in the first step we have to discretize the entire structure into convenient number of sub-elements. Okay. After that we have to number the nodes and elements. Two elements oda intersection point is called as node. Engella nodes fix pannanum appadina material property change agara portion, cross sectional change irukka portion and load engella apply agudho andha points ella must be considered to be nodal points. Okay. The given data is the Young's modulus value 200 gigapascal in terms of Newton per mm square, that is 200 into 10 power 3 Newton per mm square. Okay. It is asked to find out the nodal displacements for a given loading condition 2 kilonewton. We can discretize the entire structure into 3 sub elements. Okay. So the first element is this. And since the 2000 Newton, that is 2 kilonewton force is applied at the midpoint of the second section of the given stepped bar, we have to fix a node at this point. Okay, so there will be 3 elements and 4 nodes for a given case. Okay, this is first element, this is second element, and this is third element. So this is first nodal point. The intersection of first and second element is the second nodal point. The intersection of the second and third element is the third nodal point, and the last point is this node 4. To solve the problem using finite element equation, we have to formulate the stiffness matrix for each element. The stiffness matrix for the first element is K1 is equal to A1 E1 by L1 into 1 minus 1 minus 1 1. Here A1 is the cross-sectional area of element 1, that is pi by 4 d square. Okay, the diameter of the first section is given as 5 millimeter. So the area of the first element is 19.635 millimeter square. Okay, and we can calculate the area of the second and third element also. The diameter of the second and third element is given in the problem as 7 millimeter. So pi by 4 into 7 square is 38.4845 millimeter square. Okay. So now we can substitute the value of A1, E1 and L1 in the stiffness matrix formula. So A1 is the area of the first element, that is 19.635 millimeter square. Young's modulus of the first element is 200 into 10 power 3 Newton per mm square, and the length of the first element is 200 mm. Okay. On substituting this, we can get the value like this: 19.635 into 10 power 3 into 1 minus 1 minus 1 1. After finding out the stiffness matrices for each individual elements, we have to assemble all of them to make the global stiffness matrix, for which we have to keep a constant value outside of the matrix. For that, we can keep 10 power 3 in the outside of the matrix. Then in the inside of the matrix, there will be 19.635 into 1 in the first term, 19.635 into minus 1 in the second term. Likewise, we can arrange the matrix. Okay. Now considering the stiffness matrix of the second element, the formula is A2 E2 by L2 into 1 minus 1 minus 1 1. The area of the second element is 38.4845 millimeter square. Young's modulus value for the second element is also 200 into 10 power 3 Newton per mm square, divided by length of the second element is 100 millimeter into 1 minus 1 minus 1 1. So this becomes 76.969 into 10 power 3. So by keeping 10 power 3 in the outside of the matrix, in the inside there will be 76.969 minus 76.969 minus 76.969 and 76.969. Okay, the first element is obtained by connecting the nodal points 1 and 2. This stiffness matrix corresponds to the nodal points 1 and 2, so we can mark the rows and columns like this: 1 2 1 2. Okay. Similarly, here the stiffness matrix for the second element corresponds to the nodal points 2 and 3. Okay, so we can note the elements as 2 3 2 3. Okay, considering the stiffness matrix for the element 3, that is A3 E3 by L3, by substituting the values of area, Young's modulus and length of the third element, we will obtain the stiffness matrix K3 as 10 power 3 into 76.969 minus 76.969 minus 76.969 76.969. The third element is obtained by connecting the nodal points 3 and 4. So this matrix corresponds to the nodal points 3 and 4. We can mark the rows and columns of the stiffness matrix K3 as 3 4 3 4. Okay. Now we have formulated the stiffness matrices for all the individual 3 elements. Now we can assemble all the stiffness matrices to get the global stiffness matrix. We have kept 10 power 3 as the constant value outside the matrix. This is the assembled stiffness matrix. Okay. In the first stiffness matrix, this is the element 1 1. Okay. This is element 1 2. This is 2 1. This is 2 2. Okay. Similarly, in the second stiffness matrix, this is element 2 2, this is 2 3, this is 3 2, this is 3 3. Okay. In the third stiffness matrix, this is 3 3, this is 3 4, this is 4 3, and this is 4 4. Okay. Since there are 4 nodal points in the considered one-dimensional bar element, the global stiffness matrix will have the size of 4 cross 4. Okay, so in the 4 cross 4 global stiffness matrix, each element will be obtained by considering the corresponding element in the individual stiffness matrices. So in the 3 stiffness matrices, எங்கெல்லாம் 1 1 element இருந்ததோ அதெல்லாம் எடுத்து கொண்டு வந்து இங்க substitute பண்ணா, that will be the 1 1 element for the global stiffness matrix. So here in the first stiffness matrix, 1 1 element is 19.635. Second stiffness matrix la 1 1 element இல்ல. Third stiffness matrix லையும் 1 1 element இல்ல. So அதனால 1 1 element in the global stiffness matrix will be only 19.635. Okay. Then 1 2 element is minus 19.635 in the first stiffness matrix. In the second stiffness matrix, there will be no 1 2 element. Here also there will be no 1 2 element. So 1 2 element is minus 19.635. So considering the 3 3 element, okay, that is this 3 3 element in the stiffness matrix 1, there is no 3 3 element. In the stiffness matrix 2, this is the 3 3 element, that is 76.969. In the third stiffness matrix, the 3 3 element is 76.969. So by adding these two, we can get the 3 3 element for the global stiffness matrix as 153.938. So like this, we can consider all the individual elements presented in the element stiffness matrices and arrange them to form the global stiffness matrix. Okay. So the general finite element equation for structural problems is K into U is equal to F. Here K is the global stiffness matrix, U is the displacement matrix, and F is the force matrix. Okay. Here the global stiffness matrix corresponding to the given problem has been formulated in the previous step. We can substitute that K here, and here 4 nodal points are considered. So the displacement matrix will be U1, U2, U3, U4, and the force matrix will also like this: F1, F2, F3, F4. Okay. Next, we can consider the boundary conditions of the problem. In the problem, node 1 is fixed. Okay, so there will be no displacement. So U1 is equal to 0. But the nodal points U2 and U3 are not fixed. So U2 not equal to 0 and U3 is not equal to 0. Okay. Then node 4 is fixed in the problem. So there will be no displacement. So U4 is equal to 0. Okay, then considering the force condition, only at the third nodal point a force of magnitude 2000 Newton is applied in the positive x direction. So at the remaining nodes F1, F2 and F4, the force values are 0. Okay, now we can apply these boundary conditions in the finite element equation. Okay, here U1 and U4 values are 0, so we can neglect the first row, first column of the matrix and the fourth row, fourth column of the matrix, because U1 and U4, that is the displacements corresponds to the nodal points 1 and 4 are 0, so we can neglect the first and fourth rows and columns of the matrix. Okay, so this matrix will be simplified as 96.604 into 10 power 3 U2 minus 76.969 into 10 power 3 U3 is equal to 0, and minus 76.969 into 10 power 3 U2 plus 153.938 into 10 power 3 U3 is equal to 2000. So on solving these two equations, we can get the displacement values U2 and U3 as 0.0172 millimeter and 0.0216 millimeter respectively.